All right, so here we are with thermochemical equations, a definition. A definition that's going to be pretty handy to you because you've got to figure out when to use these particular problem-solving techniques. So let's talk about things you're going to be looking for. So first one you're going to be looking for is called delta H. We talked about that before, delta H, but right here, there's a delta H right after a balanced equation, which means that this would be a thermochemical equation. All right, so delta H is the first thing you're looking for. Second thing you're going to look for is, it might seem kind of odd, but states of matter. So states of matter are shown in a lot of equations, but in these thermochemical equations, states of matter are particularly important because if you have, for example, a solid here, and you would change that to, let's say, a liquid, it would have different values. So the heat values associated with a solid or a liquid or a gas can be very different. The biggest thing students run into is water, because water can also obviously be ice, regular liquid water, or water vapor, and that can create a problem because each of those can have different values. And so when we're looking at thermochemical equations, states of matter are going to be important. And so the last thing that you could run into is a fractional. So a fractional, didn't do a very good job with that N. A fractional coefficient. And so coefficients, if you remember, are, I'm going to sneak this out of here real quick, give myself some more space. So your coefficients, guys, are the things in front, right? So this should not be something that you're like, hey, I don't know what the heck these are because we've been balancing forever. So fractional coefficients, what the heck does that mean? Well, that means that you can use things like 1/2. And things like 1/2 become pretty common when we're doing thermochemistry because we are in situations often where we have to get a specific chemical to stay a 1. So in order to balance everything else, we may have to use a 1/2. You were never allowed to use a fraction in balancing before. So, but now, this is something new, something you weren't allowed to do, using a fraction to balance out a reaction. So anyway, these are things you're going to be looking for when you're trying to figure out if you got a thermochemical equation. So, all right, so we're going to go to an example. So it says, this represents the decomposition of 2 moles of mercury 2 oxide. Write a thermochemical equation for the decomposition of 1 mole. Okay, so what we're doing is we're going to reduce one of the values to 1. Well, that is going to be this mercury 2 oxide, right? So we just find that up here, and it is right here. And we have to get that to be a 1, because basically they're saying, hey, change that to 1. That's what they're saying. They're saying change the HGO from a 2 to a 1. That's what they're saying, right? So first thing you got to learn is that anything that you do over here, you do to this. So anything you do to the formula, you do to delta H. So, any change to the formula, you change the delta H. So whoops, we don't want that. So any formula, or I guess we should say equation. So any change to the equation, so any change to the equation, you go ahead and do the same thing. You're going to do the same to your delta H. All right, so whatever you do to the equation, you do the same thing in delta H. So if we've got to change this value to a 1, so I'm just going to rewrite it. So I'll go 1. And I'm going to write the 1 down even though I normally wouldn't, just to show you guys what the heck I'm doing. So 1 HGO, arrow, 1 HG plus 1/2 O2. So what am I doing here? Well, if I got to get this to be a 1, I divide everything by 2, right? So, you're going to divide by 2 in order to get that value to a 1. Because remember, what we're looking for is this here. Whatever I do to this, I just do the same thing here and here. And I also do the same thing to my delta H. So whatever I do over here, I do to the delta H. And so we can go ahead and write that down real quick. Let's write that delta H down. So delta H would then be, and I think it's good to write the plus sign every single time. I don't think it's smart to just write down 181.66. I think it's good to write down that plus sign so we remember what we're doing. So that's what we're doing right there, right? Dividing everything by 2. So let's go ahead and rewrite it. So the final answer would be HGO as a solid, arrow, HG as a liquid, plus there's that fraction, right? We said that those are okay now. 1/2 O2 as a gas, and then you have to have a delta H with the thermochemical equation. If you don't, that's a big problem. So we take the 181.66, we divide it by 2, we get 90.83. 90.83. And then delta H values are kilojoules, but they're technically kilojoules for each of these values here. So you get 90.83 kilojoules for 1 mole of this, 1 mole of this, and 1/2 a mole of that. So that's what that means. So if you have these exact chemicals, you're going to get 90.83, but that's only for 1/2 a mole of oxygen. So, okay. So slide down here. So it says, under ideal conditions, when 1 mole of ethanol, and it gives us the formula, gas is burned, it produces carbon dioxide, water, and 13.67 kilojoules of heat. Write an equation for this. Well, this is going to need to be a thermochemical equation. So let's go ahead and note that it's not just an equation, but a thermochemical equation, because they gave us this. So pause the video and see if you can figure it out. All right, I'm going to go ahead and work this through for you. Let's see if you got it right. Okay, so we are hopefully getting better at combustion. So I want to point out one really, 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 really important thing. It says you get 1 mole of ethanol. This is ethanol. That means I only get 1 mole, which means that the value here has to be a 1. I have to keep that a 1. That's the problem with some of these, is that you're forced into certain balancing situations. That has to stay a 1. So oxygen, carbon dioxide, and water. Now they did give us the fact that it was a gas, so I probably should put that there. That's a gas. That's a gas. So let's do it like that. Okay, and then we get a delta H. And they told us that the delta H was 1367. So did the heat go in or did the heat come out? That's what you have to ask yourself. It also says the word and, right? So it's like saying and you get that much energy. So the word and is super important here. And so let's think about it. Every single time you have combustion, we talked about this earlier, combustion is something that's always exothermic. So we want to remember that combustion is always exothermic or negative, right? So negative. So delta H here would be negative. Don't forget the negative 1367 kilojoules, because they don't give you the negative in the problem, but you have to understand combustion is always negative. And then from a balancing perspective, looks like we're going to need 2 carbons. For the 2 carbons there, we have 6 H's. So we're going to need a 3. And then we're going to come back and finish this up. So 3 and 6 is 9, but there's 1 there. There's 1 hiding right here. So that's 10. And so we'll go ahead and sort that out with a, sorry, no, I miscounted. That's not correct. Miscount. That's 4 and 3. Sorry, that's 7. So there's over here we have 1, and then sort of fix that. All I've got to do is put a 3 here. Sorry for the miscount. Happens though. So 6 O's plus 1 is 7. 2 times 2 is 4, plus 3 more over here. That's 7. Everything's balanced. So this right here, this is what you would report your answer as, all of that stuff there. All right. Key takeaways. Combustion is always exothermic. They don't give you the sign when you do a problem. It's not automatically given to you. They may assume you know acid base is negative, combustion is negative. You have to include a delta H with any thermochemical equation. So if you did everything here but didn't do this, you get the problem wrong, because it's not a thermochemical equation. It's just a normal equation. So, all right, we'll stop there. Some key takeaways here and some stuff that definitely can start to see on a test or an assessment.